So welcome everybody to our February LOF&BE webinar. I'm Sarah McAllister. I'm hosting these with Sam Manzello and Sayaka Suzuki. Today we've got some great student speakers for us today. And so the usual protocol is to everybody to stay on mute till the end, and we'll do questions through the chat box, or feel free to unmute and chime in. Just remember, you'll be recorded for the YouTube. And if for those who've missed it, or those who've missed it, we will be posting this on YouTube afterwards. So without further ado, I'm going to introduce our first speaker, who is Natalia Flores. She is a postdoc researcher in the Fire Research Institute unit, a Fire Engineering Research Unit at Stellenbosch University. So without further ado, go ahead, Natalia, and get us going.
Okay, so good day, everyone, and thanks for the introduction, Sarah. I'm Natalia Flores Quiroz, and I will be talking about my PhD research. The topic was fire investigation for informal settlements. And just please keep in mind that this research project was focused on informal settlements located in Cape Town, South Africa. Okay. Okay, so first I'm gonna tell you a bit about myself. I am from Chile, and in there I study electrical engineering. After that, I worked for 5 years in the design of fire protection systems for the mining industry. Later, I decided I wanted to specialize in fire safety, so I joined the Master of Science in Fire Safety Engineering program at Ghent University in Belgium. And after that, I continued with a PhD at Stellenbosch University here in South Africa. I applied for the position here because I found the topic to be very interesting. And coming from Chile, I was very familiar to informal settlements. And I thought that this research could hopefully have an impact on many people around the world. Okay, so first of all, what is an informal settlement? And in case you're not familiar with this term, informal settlements are, are typically low-income communities characterized by poverty, poor infrastructure, as we can see here. We can see that, for instance, this dwelling is constructed with metal sheets, some timber here, cardboards. We can see even some leakages here. We can also see in informal settlements very high dwelling density, right? We can observe here they are very close one to the other. Additionally, there's a lack of basic services such as water supply or electricity supply. So sources of energy such as open flames and paraffin are often used. The motivation for trying to gain a better understanding of informal settlement fires is the impact that these have in people's lives. We can see here in this graph that even when the number of formal settlement fires is almost the same as informal settlement fires, the number of fatalities is much higher in informal settlements, more than double. And this could be due to the fact that one single event can affect several homes. For large incidents, more than 2,000 dwellings can be affected and more than 10,000 people can be displaced. Additionally, almost 40% of all fire causes in informal settlements are undetermined. And this might be due to the lack of investigation of this type of fires. So the main research question of this work was, what happens in informal settlement fires? And for that, we first need to answer, how can a fire investigation in an informal settlement can be conducted? Is it possible to determine the fire origin, fire spread in an informal fire event by conducting a fire investigation? And what are the causes of informal settlement fires? So here's the methodology that was used to answer these research questions. First, a framework for fire investigation in informal settlement was developed. And this framework was based on fire investigation techniques used for enclosure fires and wildland fires. Then I analyzed a real informal settlement fire that was recorded by a CCTV camera. The camera captured the entire event, and this allowed for the analysis of the fire spread, the residents' actions, and the firefighters' operations. Then this framework was applied to 3 large informal settlement fires. including the one that was recorded by the camera. This allowed to identify the applicability and the limitations of the framework. And finally, in order to obtain information about the fire causes, a survey conducted to more than 2,000 dwellings after a large fire incident was analyzed. And from here, the residents' risk perception was associated to potential fire causes. So now I'm going to go through the main findings of this work. Okay, so first, the considerations that we must have when conducting fire investigation in informal settlements. So due to the construction methods, the material used, and the close proximity between dwellings, it is very likely that once a fire starts, it will spread to other dwellings. And there won't be much physical evidence left at the scene. As we can see here, it's mainly metal sheets, right, that we are seeing here after the fire. Furthermore, the residents will start the rebuilding process very soon after the fire. So this means that the time to conduct the fire investigation is very limited. Here we have these 3 images. This was taken 4 days before a fire. This was 1 day before the fire, and this 18 days before after the fire. So we can see that the next day there's nothing left. So if you wanted to check something, you should have done it right after the fire happened. Okay. So with regards to the residents' actions during the fire, in the first stage of the fire, most of the efforts are placed in the firefighting activities. We can see here that men, women, and sometimes even children participate actively on this. Once the fire starts spreading to other dwellings, the residents' actions starts to diversify, and most of them start saving their belongings. Okay. It was possible to see in the video re-entry behavior many times, and also some people evacuated and stay here looking for their belongings, but you could see people coming and going all the time. As the fire kept spreading, these activities continued, but we can see only men doing the firefighting activities, while women were mainly worried about saving their belongings and staying in this safe area. This behavior was very similar to what has been observed for residential fires in previous research. The firefighter response to informal settlement fires can be affected by late notification of the fire. For example, in one of the cases, the phone call to notify about the fire was done 1 hour after the fire started. Another factor is the difficulties in reaching the affected area. So it's very difficult to transit through the narrow roads and to the dwellings, especially with all the firefighting equipment. Right? There's also the lack of water supply. It will be very difficult to find hydrants in these settlements, and if they are, it's very likely that they won't be operative. And finally, the hostility from the residents. During the interviews with the firefighters, they mentioned that they were attacked and sometimes even mocked when attending to these fires. Here, we can see the 3 large fires that were studied. This one involves 40 dwellings, this one 80, and this one, I think, a bit more than 1,000. And through the analysis of the fire scar, the ambient conditions, the topography, the firefighters' testimonies, it was possible to identify that the fire spread was mainly influenced by the wind, the firefighting actions, the availability of combustible material, and the close proximity between dwellings and the topography. This table presents a comparison of the fire spread rates estimated on this work. The ones in this work are the ones in orange, and others from other similar work, these ones in green and in blue. So the green ones were obtained through the analysis of real fire events, while this blue one was obtained in an experiment that involved 20 informal settlement dwellings. So if now we focus on the linear spread rates, we can see that for the real fires, that is this one and these ones, the linear spread rates are very similar, going from 1.2 to 1.7 meters per minute. Now, if we focus on this one estimated with the framework, we can see that they are very low in comparison with the other ones. And this is due to the difficulties to reconstruct an accurate timeline to the event. So even if we look at this one, that is the same case, this one analyzed with the video and this one with the framework, we can see the difference there. And this one is from the experiment is much higher. And this is attributed to the lack of firefighting interventions during the experiment. For the risk perception, 2 questions were formulated. What do you consider to be the greatest risk in your household? And what do you consider to be the greatest risk in the settlement? And we can see here that the answers varied depending on the risk target, if it was the settlement or if it was the household. So the biggest difference are observed in those items related with irresponsible behaviors, such as drinking, cooking, or smoking. An extreme case is irresponsible drinking behavior, that is here, with 51% of the people indicated that it was a big risk for the settlement, but only a big risk, a 0.6 indicated that it was a risk in their own household. A similar thing happened with irresponsible cooking. And also something interesting was that almost none of the household indicated that there was nothing risky in the settlement, while 6% indicated that there was nothing risky in their own household. So now I'm trying to link this perception with the fire causes. And this graph aims to determine if the risk perception of the inhabitants of informal settlements and the firefighters are well represented by the national statistics. The information for the firefighters' risk perception was obtained from different research. So here we have these 9 categories that are part of the official fire causes. And these 2 that were included to highlight the fact that residents and firefighters mentioned that these factors were important, but these ones are not included in the national statistics. So if we look at here, it seems like the only category that it has like a good level of representation is electrical faults. And then the rest is all over the place, right? And we can see something very interesting happens here. If we go to the open flames category, this one, it appears that the inhabitants don't perceive it as a major problem. However, according to the statistics, almost 20% of the informal settlement fires are caused by open flames. But now if we look at cooking, heating, or lighting, we can see that there's concern from the inhabitants, but it's not represented in the statistics. And this happens because in informal settlements, open flames are used for cooking, for lighting, and for heating. So the fact that there's no more details about the use of these open flames, it's a big problem because we don't know where the exact problem is. We don't know if it's cooking and lighting. So yeah, and maybe for formal houses, this is okay, but here in informal settlements, it doesn't really work that well. Okay, so from this graph, we can see that the national statistics are not accurately capturing the causes of informal settlements fires. And to finalize, I would like to mention the benefits of investigating the real fire events, and it allow us to understand the fire in a holistic way, to then identify new problems like different fire causes, type of constructions. For instance, now they are very worried about the 2-story dwellings in informal settlements, to develop or validate fire spread models, to enhance firefighters' response, and in general, to develop better fire safety interventions. So thanks. That was my presentation.
Thank you, Natalia. That was really interesting. So if anybody has any questions specifically for Natalia, go ahead and put them in the chat box. We will hopefully have some time at the end to do some other chatting and discussing when we get there. So we'll do a little now and then hopefully some later. I'm actually like amazed at how quickly these communities rebuild after a fire. I mean, that's amazing. That after
it's impressive,
like
yeah.
18 days, you can't tell that anything happened. So David Rush has a question in here about how you define irresponsible drinking behavior.
So when I worked with the survey, it had a lot of answers. It was an open question, so I had to define the categories. So many of them said, like, for instance, they would go drinking and then they would start cooking. So in that case, I would consider that the problem was the drinking and not the cooking. Many of them just say, like, it's alcohol abuse. They mention a lot of alcohol abuse, or the fact that the taverns, shivins, they call them, were open until very late. And it kind of makes sense with some of the things that I've heard, like the riskier environments or the riskier households are the ones where single men are living, because they usually get very, very drunk. So yeah, I went through all the answers, and those related directly with alcohol, I include them as irresponsible drinking behavior.
Oh, gotcha. Interesting. Very, very quickly here. David Rush raised his hand. So go ahead, Dave, if you want to chime in and ask a question.
Yeah, I think it's just to kind of respond to that. So I think, it's a catalyst. So irresponsible drinking behavior is more of a catalyst for fire rather than a cause of fire. Like, yeah. I definitely go out and have a few beers and maybe not have that in a responsible manner, but then, I'm able to go home and cook in a safe environment if I have been drinking. So it's more about actually the fact that they don't have safe cooking practices or materials or kind of systems, which when they are not able to control their functionality properly because they're inebriated, actually then cause the fire, which may be why you're also seeing that in your statistics, you're seeing a higher prevalence of open flame being the cause of fire rather than not having this other factor of irresponsible drinking behavior. So I think, yeah, that's just my.
It's also important to mention that that's very difficult to quantify and to include in a statistic, because you cannot go and, like, I don't know, get people some tests to see if they are really drunk or anything like that. So from what I saw, what they do in the US is that they include they think there could have been alcohol involved in this, whatever accident it was. So it's not included like in the statistics, in the national statistics, but there's some information about it that can be tracked later. And it's also very interesting because when we had the lockdown here in Cape Town and there was an alcohol ban, the number of informal settlement fires went down a lot. Like I can't remember exactly, but maybe 40% less. I can't really remember. So then you could see that, well, there were a lot of measures. So one of them was the alcohol ban. But yeah, for me, it was kind of interesting to see that.
It's a very interesting point. I didn't even think about the whole being drunk and trying to cook. I just sort of figured it was the, oh, hey, watch this, hold my beer type of irresponsible drinking behavior. Very, very brief. I have one other quick question. You mentioned that there were hostilities towards firefighters. Do you can you comment on why that is?
So it seems that people get very mad because it takes a long time for the firefighters to get there. And once they get there, because the fire is already developed, they start breaking some of the dwellings that are not burned in order to create fire breaks, or they are trying to put down to extinguish a fire in one house, in one dwelling that is not yours. So they start cutting the hoses, trying to redirect the water to their houses. And then they've been like stoned because they are too late. And, and as I mentioned, even marked sometimes. Yeah. It's not like very particular. It happened a lot of times. It's something that the firefighters are scared about going to these events.
Yeah, I understand it because they're trying to do their jobs, but unfortunately, it's destroying people's houses in the process. That makes sense. Okay, great. So that's perfect timing to move on to our next speaker. Thank you, Natalia. That was awesome. So Ruben, if you want to go ahead and share your screen, and I'll get you introduced here. So he is a PhD student at the Western Norway University of Applied Sciences. He works in the Fire Disasters Research Group. It looks like you're ready, so I'll get out of your way and let you go. Thanks, Ruben.
Thank you. Thanks for the opportunity. So, well, the title of my presentation is Improved Home Fire Risk Warnings Using Cloud-Based Weather Data Services. and I was requested to do a just quite quick about page. So, well, my name is Ruben. I live in Haugesund in the west coast of Norway. I work in this research project known as Dynamic, reducing fire disaster risk through dynamic risk assessment and management. But it's together with the Western Norway University of Applied Sciences, so that's where I have my office. My motivation for going into this task was kind of the opportunity to combine both practical work and theoretical work. So I work with risk models and implementation and a notification system, but I'm also able to participate in prescribed burns and to see the changes in in the landscape, both before and after a fire. Yeah, okay. So the content of this presentation, I was also asked to just report a little bit on the current challenges in Norway. So I will do that with respect to the Norwegian West Coast and the heathlands, wild and urban interfaces that we work with within our project. And then I think that I will speak something about the cold climate fire risk indication model developed within Dynamic. And I will use some case examples here of the fire in Lærdal 2014 and the Marshall fire. So, well, could probably skip this one, but just to mention a few, what's going on. Conditions have changed. We see changes in climate, ways of living, land management, and the results are, among others, increased biomass, increased WUI areas, and also the number of houses exposed to this risk. And also we see that, numbers of areas exposed to wildfire in the first place increases. So we're not too accustomed to wildfires in Norway, but we see an increasing number of events still. What we do see or not see, this picture was taken in 1975, just nearby the university at an island known as Karmøy. So this was 1975. There was still some livestock going around at this time. Some years later, 1993, it's the very same place. And in 2019. So things are changing, and they change not so fast, perhaps, that we notice on a daily basis, but still you see the changes are quite extreme. So this area now is just junipers, Sitka spruce, other pine trees, and yeah, it's obvious that something has happened. When reporting on the situation in Norway with respect to the cultural landscape and the heathlands, I will use a case. There was a fire at Sotra, an island outside Bergen. So as the arrow shows it, at the west coast of Norway. This happened last year, 3rd to 4th of June. Then it was kind of put out, but came back at the 10th of June due to peat fires, so difficult to extinguish. So Sotra is an island. You can see the fire origin here. The fire started at the bottom of an inclination, and quite early in the developing phase, it actually crossed the road due to, it seems like, quite high juniper trees, 2 to 3 meter tall. So it kind of quite quickly got enough strength to cross the road with embers and so on. So it kind of spread out through the landscape here, as can be seen with the red arrow. So the winds were shifting, high winds, north-northwest, and shifted to northwest. So, the landscape was full of old Kaluna, juniper, rocks, pines, and Sitka spruce. And I think this is something that many of you probably would recognize. The land management kind of stopped due to people, farmers, just going into the industry, working in the industry because it's better paid. So the livestock that used to walk these areas, well, they disappeared. Particular risks at the Sotra fire was settlements in the north and in the west. So this is not the worst I've seen, but still they have pine trees, Sitka and juniper going into the settlements, no defensible space, kind of juniper going into the well-ventilated porches and so on. Total area burned about 5 square kilometers. Up in the north, the red circle. The fire came pretty close to the settlement, but nothing in particular, no fire spread into the settlements then. But it was close enough. I mean, with respect to the winds and everything, it was close enough to be able to spread, but fortunately it didn't happen. Along the west side of the island, the situation was a bit different. So a house was lost and a cabin was lost. Yeah, I think the pictures speak for themselves as well. And yeah, as you can see here, the houses are just like overgrown. Trees, juniper, unmanaged heathlands. And well, I think it's good to show the situation through pictures, but this is still not, it's not the worst that I've seen. I attended a prescribed burn at Karmøy last year, Skår. So it's been a while since this area was used for grazing. There were livestock here before. Now it's all juniper, so it burned quite well. Cattle was reintroduced when we finished the session after some months. Yeah, and well, that's kind of the first part, reporting on like the situation here in the cultural landscape of the heathlands, overgrown, that is. A number of houses exposed to or centered in the wild and urban interface. But now I will do kind of a change, because as the title of the presentation, like improved home fire risk warnings using cloud-based weather data services, some of the things that we work with in Dynamic is developing risk models and notification systems. So, well, yeah, you just have to go with the change here in topic. So now I'm on to the modeling part. What we do is we try to collect local weather data, and we do that through the Norwegian Meteorological Institute. So they offer weather data, both historic weather and forecast weather. And this is high grade weather data. So this is a very good infrastructure. So we're utilizing existing high grade infrastructure instead of trusting in, for instance, wireless sensor networks and collecting local data, which of course is a good solution. But you know, choosing an existing infrastructure as our basis for data, we are able to implement it in the data into the model, and we can offer this you know, for a low price. So this could be like free for people, and we can develop as we go and you know, push this into, for instance, the fire department, so they are able to use it for risk assessments or something like that. Okay, so we have the local weather data, we implement it into our models, and we compute the local risk. And within Dynamic, we focus on wooden homes, like the first house catching fire, and we focus on fire spread between houses, and we also focus on fire spread in the wild and urban interface. And our main goal is to combine different models to end up with a conflagration model. And yeah, this session here will focus on the first model then that we've developed. This is a wooden homes fire model. So it tells us something about the risk for the first home catching fire, and the model is developed by my supervisor, Torgrim Log. So this model that I will speak about now is implemented into a cloud-based system and is kind of operational as a beta version. So the concept of the model is kind of to treat a single house or each house just as, you know, you treat each tree in a fire wildfire model. So we say that each house is kind of a box with a vapor barrier, and there is an indoor cladding, wood panels. You have some air exchange with the surroundings, and you have some moisture supply within from people cooking, breathing, taking a shower, and so on. And so the model from first principle physics and mathematics, I will not go into this, of course, but just at the end here, you'll see that we model the change of water concentration inside the building with time as something that depends on the air change rate, the moisture supplied or absorbed by the walls, and the moisture supply within the home. So yeah, that's the approach, and we've utilized the model for the Lærdal fire and the Marshall fire. This was just kind of to show a picture of the Lærdal fire here, outlined the house, 18th, 19th of January. This is the flames that you see here belongs to this house. So the flames are all horizontal. There were quite heavy winds during the Lærdal fire. Nevertheless, what we want to do is then to be able to say something about the risk, both today and tomorrow and after tomorrow, and try to predict upcoming risk peaks so that fires like the Lauderdale fire can be somehow prevented. The Lauderdale fire, which is a town fire, started off as, you know, a house fire, but it developed so fast that even though the house was next to the fire station, they didn't manage to get control before the fire was just the whole house was engulfed in flames, both inside, outside. And, you know, with storm strength winds, it was a difficult task. Wooden homes at the top here, conflagration, as I mentioned, would be kind of the goal when we combine different models, which we have not developed yet, but working on. Running the model, 2 case examples, Lauderdale and the Marshall fire. So yeah, I'll explain that when I show you the graph here. So what we do with the model, I showed you the general concept, you know, about the box and the indoor wooden claddings, and that we say that we have some kind of water concentration. When we do this modeling, we model the indoor moisture content of the wooden wall panels. So we kind of achieve a value for the indoor fuel moisture content. And we correlate the fuel moisture content of the indoor cladding with the time to flashover for the house. So that is based on some experiments done at the Western Norway University of Applied Sciences, quarter scale experiments, quarter scale iso-room experiments. And, you know, most of us working with fire know that this is not an exact science. You know, you can't predict on the minute the time to flashover. It's impossible. Well, you can predict the time for a tree to catch full of fire, neither, but still we rely on the wildfire models. So this is the same principle, same working principles as a forest fire model. But what we utilize is then the time to flashover, and it doesn't matter what the values along the axis here is. It's kind of what does the model tell us, because the model is validated with regards to the modeling of the indoor fuel moisture contents. So what we see when applying the model for some time, we see that, okay, we experience, for instance, that 4 minutes, time to flash over 4 minutes, that is kind of a critical limit. Fires that appear when we measure when we model the humidity to be less than 4 minutes, well, that is bad. So conditions are critical when we go below 4 minutes. So we kind of have to run the model and to see how the scales relate to real life events. But that is our understanding now. When you go below 4 minutes, or the major fire that we investigate in which we use the weather data available, we see that 4 minutes, it goes below 4 minutes. And as you can see here, this is the case for the Lauderdale fire as well. It went below 4 minutes time to flashover at the day of the fire, and the fire developed too fast for the fire department to intervene. And they spoke about the Lauderdale fire as an extremely dry case. You know, at the time of the Lauderdale fire, it was so dry in Lauderdale, and that is true. It was very dry on the outside, but they first started to speak about this extreme fire development in the first house that catched fire. You know, if the first house that caught fire hadn't caught fire that fast, they would probably managed. But when we modeled the conditions in Lauderdale from 2014 to 2021, we experience, or we do see, as shown in the graph here, that the indoor conditions in Lauderdale was not at a particularly low in 2014. It gets just as low pretty much every year. So the extreme fire development for the first house reported doesn't seem to be a particular case. So the outdoor conditions and the belonging fire spread that followed, of course, was something else. Marshall fire, just took some weather data from Denver Airport and ran through the model for the Marshall fire here, and we kind of see the same. We see the same thing here. The value drops in the beginning of December, and as it gets, you know, cold and the low outdoor humidities, it gets even, you know, the potential for drying out the indoor wooden materials is increased, and so we see values below TTF 4 minutes. So here you see values drop below, and the fire of the Marshall fire, it was 30th of December. So it's, yeah, I think this is interesting. Yeah, very strong winds. So that is something that would increase the risk, of course. Bad combination. So that is probably something that would contribute to a conflagration instead of just a single house fire. And well, yeah, that was it. Is there more time? No, I just brought that in case I had more time, I would continue, but I see that I've passed my 15 minutes. So thank you. The questions?
Yeah, thanks, Ruben. That was a really great introduction to the whole fire problem, especially in Norway there. There are a couple of questions in the chat box. So Dan Gorham writes, in regards to the weather data, do you have measurements at ground level within the settled areas? The complex terrain within buildings create complex winds. And I understand this is challenging to measure, but curious if the data you consider includes it.
Yeah, that's a good question, good point. So we have the data that we gather. We need for the model to run, we need both outdoor humidities and we need outdoor temperatures. And not all weather stations keep a track of the outdoor humidities and temperatures, and especially not for the time series that we need. So we rely on the nearest weather station to give us that data. And of course, it's something different when you need forecast data, because forecast data is something else that is dependent on the resolution of the models that is predicting the weather in the first place. But when we use historic data, it would be the closest weather station that provide these data, and it's not too far. You don't have to go like tens of kilometers away. But yes, we do not have like just in the middle of a settlement, not necessarily. But we have successfully also implemented the model utilizing net atmo weather data. So that would be weather data collected from weather station, private weather stations. And these weather stations are located within the settlements. And also the Norwegian Meteorological Institute in Norway have utilized these weather data from private weather stations in the predictions of at least temperatures. So yeah, we try to use the weather data that is available as good as possible, but of course there will always be differences, and topology will affect, for instance, winds and such. So it's a good point. Yeah.
Yeah, and yeah, you're kind of in a weird situation there, right? Where, because you say you want to use the publicly available free data, and that's what you get, right? So
yeah, that's what you get. But still, it's there is a difference when you use predicted data, because the predicted data is based on the data that comes from the measuring stations, right? And they predict it within the models, and they have a better opportunity to predict local weather when they use the models. So one of the things that we are investigating is, instead of using the measured data at a local station, we might use the predicted data just prior to the time that we shall compute the values, because the predicted data would be more like interpolated data from sophisticated models between the different weather stations that do the actual measurements and recordings. So that appears to be the more reasonable way to go, but we're still doing some testing with regards to that.
Cool. Neat. Dan also had one other quick question, is for time to flashover, is there an assumed incident heat flux or a thermal parameter?
There is so these, there was quarter scale so the thing is that we come up with the time to flashover based on quarter scale room iso-room fire tests, and these iso-rooms were tested during different moisture conditions for the internal cladding. There was the same fire size in all the different tests. I can't remember the size of it, of the fire, but I mean, this is quarter scale fire test, so the fire was not too great. But the important part here is not the size of the fire; it's how the different humidities react to and develops with regards to the time to flashover. So what do we see with regards to the moisture content and the time to flashover? And if we've chosen, for instance, a different fire size, the only difference that we would see is, as I mentioned, that the values along the x-axis of the time to flash would change. And so, for instance, we would have that, okay, so 6 minutes would be the critical limit that we see for, that you should be aware that increased or high risk values. So, if we change the fire size, we would only change the values along the x-axis. So with our approach, which is risk-based, it doesn't actually matter what the value of the fire was. We just had the same fire through different scenarios with different moisture contents.
Gotcha. Sounds good. Well, thanks again, Ruben. Dave Rush just typed in another question in the chat box, which we will hopefully get to at the very end. If not, I'll connect you to, and hopefully you can get to it. So without further ado, let's do our last speaker. So Simona, if you want to go ahead and start sharing your screen. Our next speaker is Simona Dossi. She is a PhD student at Imperial College in London in the Hayes Lab Research Group.
Hello there. Sorry, I couldn't unmute myself. Hello, everyone. Thank you for having me. So my name is Simona, and I will be presenting a project we are working on analyzing post-fire building inspection damage data from 2 case studies, specifically from California and from Portugal. So just a brief introduction on this topic. So wildland-urban interface fires are created when wildland fires ignite built environment that is located near the wildlands. And this changes the fire dynamics, the fire risk, and the fire impact, as the fire impacts communities directly. And researchers have been discovering a lot about these types of fires through post-fire studies, where they go and inspect wildland-urban interface fire regions and look at how the fire spread and what damage was caused and how it was caused. So I included this figure from the 4 Mill Canyon fire findings, which shows that they observed in this post-fire study, they observed buildings that survived really high intensity wildfire exposure. And they also observed many buildings, in fact, the majority of the buildings they inspected, that got completely destroyed from very low intensity wildfire exposure, as shown from the condition of the vegetation around it. So this observation showed researchers that it is the building structure and the surrounding area, or the defensible space, that really determines whether a house gets destroyed or damaged from wildfire exposure. So my research focus specifically is to look at the ignition risk of homes in the Southern European wildland-urban interface. And I included on this slide just some statistics from the 2021 wildfire impact, so just of the last wildfire season in Southern Europe. And as you can see, it's a big problem in this region. And the fire weather index is predicted to increase across Europe. So it is a problem that is expected to grow. And definitely the need for more understanding and for applying this understanding to practical solutions is a big motivation for my studies in this field. And also another reason I'm really happy to study in this field is that wildfires are a really interdisciplinary topic, and they occur in many different regions around the world. So there's a lot of opportunity for learning and interactions from people from different backgrounds. Okay, so the data analysis that we conducted, we considered 2 databases, one from California and one from Portugal. The California data has been collected from California Department of Forestry and Fire Protection since 2013 through their damage inspection program. And we only analyzed the data collected between 2013 and 2017, which comprised of 17,500 buildings exposed to wildfires. And each of these buildings were classified with a damage level ranging from no damage to destroyed. The second database from Portugal has been collected from our collaborators from the University of Coimbra, and they inspected all the structures that have been exposed to the Pedrogao Grande fire in 2017. And the paper reference on this slide actually presents this data and their post-fire inspection study. And so we analyzed 1,190 structures that were also classified with a specific damage level each, ranging from no damage to destroyed. So graphs just show the distributions of the damage levels of the two databases. And already we can see quite a big difference between the databases, as the California database is very skewed towards completely destroyed buildings, while in the Portuguese database, the highly damaged and the completely destroyed buildings have comparable proportions. So on top of the information on the damage level the building experienced, we also have some information on the building structure itself. And we specifically picked data that related to the building construction and not the defensible space or the surrounding area, just to focus on how the building features impact damage. So for the California database, we have information on the exterior building walls material, the number of window panes, the roof material, deck material, the design of the eaves, whether they're open or enclosed, and whether the building had vent screens or not. For the Portuguese data, we similarly have information on the exterior building walls material, the roof material, the deck material, and also the preservation level of the building. So this relates to how well maintained the building is, if it's clean, if there's a lot of accumulated debris on the building that could get ignited, and also if there's any breakages or openings in the building, as building abandonment is quite common in rural Southern Europe. Questions we focused on when looking at this data was we wanted to try and compare the buildings in California and in Portugal in terms of wildfire resistance. And we were wondering which one of the building features we considered are most strongly correlated to wildfire damage, both individually and how the overall building construction, so all the features together, impact the damage the building experienced. So for each building feature, we classified the characteristics as either providing low fire protection or high fire protection. So for example, for the California roof material, the two options are fire resistant material or combustible material. So the combustible material would offer a lower fire protection. And the blue lines here show the missing data in the databases. And these graphs just show the relative composition of each building feature in the two databases. And it shows that in the Pedrogao Grande database, there's a much higher proportion of building features that offer a higher fire protection. To look at which building features were most correlated with wildfire damage, we used hypothesis testing, and we set the null hypothesis saying that the damage level and the building features are completely independent, and the alternate hypothesis saying that the two variables are related. And we used two different methods to run this hypothesis testing: the chi-square test of independence and Kramer's V, and the Bayes factor. So I just have some more information on these tests on this slide. And basically the chi-square test of independence uses the chi-square distribution and p-values to determine whether there is a statistically relevant relationship between the two variables considered. And then Kramer's V is calculated using the chi-square value, and that it relates to how strong the correlation is between the variables. So the larger the Kramer's V value is, the more strongly correlated the building feature is to damage level. And the Bayes factor is just a different type of hypothesis testing. So similarly to the chi-square, it tests if there is a statistically relevant relationship. And the higher the value of the Bayes factor, the higher the probability that there is a relationship between the variables. So these are the results for this analysis for the California data. And the chi-square test of independence found that all building features have a statistical significant relationship to damage level, except the eave geometry. So based on this data, this test showed that whether the eaves were enclosed or open did not have a strong relationship with the damage level that the building experienced. And then the Kramer's V value, which quantifies how strong this correlation is for the other variables, shows us that the roof material was shown to have the weakest relationship to damage level, and vent screens followed by the number of window panes had the strongest relationship. And the Bayes factor supports these results, but it found that all of the building features have a correlation to damage level except eave geometry and roof material. So both tests agree that these two building features are the least related to damage level. For the data, both the chi-square test of independence and the Bayes factor found that all building features have a statistically significant relationship to damage level. And the Kramer's V value showed that the roof material had the weakest relationship and the deck material the strongest relationship. But they all seem to show a stronger correlation to damage level than the California data. So lastly, to look at how the overall building construction impacts final damage, we created a very simple wildfire resistance index. And for each building feature characteristic that offered higher fire protection, we assigned a coefficient number of 1, and we assigned a coefficient number of -1 to each feature with lower fire protection, and a coefficient of 0 for any unknown or intermediate options for the features. And we summed these coefficients for each building and normalized the value to a -1 to 1 range. So what we get is that each building has an index value that ranges from -1 to 1, which relates to how much fire protection their features have. So to check whether this index correlates to the damage level of the buildings, we plotted the index against the proportion of buildings that experienced a certain damage level. So in this graph, we plot the data for the California data, and we plotted the index against the proportion of buildings that were destroyed from wildfire. And the size of the circle plotted is proportional to how many buildings there are for each index value. So we see that from about -0.2, as the wildfire resistance index increases, the proportion of buildings that were destroyed decreases. So we can observe this trend for these values of the index. And for the lower values of the index, we can't see a trend, but this could be explained by the fact that there are fewer number of buildings with these index values. So similarly, this is the graph for the California data of the wildfire index plotted against the wildfire resistance index plotted against the proportion of buildings that experience no damage. And similarly, we see an increasing trend in proportion of survived buildings with the increasing wildfire index for values of the index from -0.2 onward. For the Portuguese data, we plotted the similar information, but because of the smaller sample size of the database, we in this graph, we plot the wildfire resistance index against the proportion of buildings that experienced either high damage, 40 to 75% damage, or that were completely destroyed. And we see similarly that we can kind of see a trend from the wildfire resistance index of 0.5 to 1, but we would definitely need more data to validate this trend. I would also like to note that for the Portuguese data, the wildfire resistance index only goes down to negative 0.25, and that's just because there were no buildings in the database that had a lower index value. And this is just a similar graph, but plotted against the proportion of buildings that experienced either no damage or low damage, 1 to 19% damage. So in summary, we found that the California database had a much higher proportion of completely destroyed buildings compared to the Portuguese database. Also, we found that the Portuguese database showed that buildings had a higher proportions of of building features that offered higher fire protection compared to the California database. Out of the hypothesis testing that we ran, we found that in the California database, the eave geometry and roof material building features showed either no or a weak correlation to damage level, while the other building features showed a strong evidence of correlation to damage level. And the wildfire resistance index showed that for certain values, we did see a trend that an increasing proportion of survived buildings and a decreasing proportion of destroyed buildings was observed as the wildfire resistance index increases, but more data would be useful to validate these trends. So thank you, and please let me know if you have any questions.
Thanks, Simona. That was really interesting. My mind is blown a little bit that the roof material in the California data set didn't matter that much. And that leads me to a question real quick. I don't see any others in the chat box real quick. So I'm going to go ahead and ask my question. So in the California data, were there any houses that had wood shake roofs? And maybe this is because I'm getting old and people don't put wood shake roofs on their houses anymore. But was that present in the data at all? Because I'm sound.
Yeah, no, that was a really surprising result for us as well. And the only information about the roof material that I know is that, or that they give in the database, is if the material is fire resistant or combustible. So I don't know the details of which material that would be. One of the reasons we've tried to explain this result is that perhaps it's not just the material of the roof that is important when the roof ignites, but about the shape and the kind of if it's an ember ignition, maybe the aerodynamics are really important in that as well. So only considering if the material is fire resistant or combustible might be too simplistic to look at that. That's one of our hypotheses, but we're not sure.
I gotcha. So there was no distinction between like wood, like asphalt and more like a ceramic tile or something. It's definitely, yeah. I gotcha. Well, are there any other questions for Simona in chat box? Here's one. Okay, so there's a question about what would you say are the reasons that the California database, the DINS database, has a higher proportion of buildings destroyed? That's a question.
Yeah, that's a good question. And again, I can only kind of infer. I think one important thing to know is that the two databases are very different in size, and the California database spans over a few years, and the Portuguese database looks at the one fire complex. So I think that's something to take into consideration, but also from looking at the building features, we do see that the Portuguese buildings had a lot more fire resistant or features that offered higher fire protection in terms of the materials they used. So that could be one of the reasons, but I'm sure there's more reasons.
Certainly a lot to dig into there for sure. Well, we are coming up right on top of the hour here. So I think we'll respect everybody's time and stick to the time, stick to our times. So thank you all of our speakers for great presentations. Really a great variety of talks. It was really enjoyable. Just a plug for next week, for next month, we have David Rush as our speaker for March. So everybody come tune in for that. And yeah, thanks again, everybody, and we'll hopefully see you again next month.